Welcome to Chapter 20 Practice. We have about 5 questions to get through today. I'm going to do our normal approach where we read the question and I give you some information about how to set it up. And then I want you to pause the video, attempt it on your own, and then resume to see the answer. So let's look at question number 1. This comes from problem number 43 at the back of your book. And it states sulfur dioxide is released in the combustion of coal. Scrubbers use aqueous slurries of calcium hydroxide to remove the sulfur dioxide from flue gases. Write a balanced equation for this reaction and calculate delta S of the reaction. So everything that's in the brackets after that, besides this portion right here, I actually looked up for you in the back of your book and gave to you. The idea behind this problem is that you would first set up the balanced reaction and then you'd identify all of the all of the S values, the standard entropy values that you would need to actually solve the problem. So I gave those to you. The balanced reaction that you're focusing on starts really in the second sentence. Scrubbers use aqueous slurries of calcium hydroxide to remove sulfur dioxide. So it's telling you that calcium hydroxide and sulfur dioxide react. So you'll set up that balanced reaction and fill in the products. After that, you'll use all of the entropy values that are given to you to solve for the change in entropy for the entire problem. So go ahead and pause here and then come back to see your answer.
All right, first step is I wrote down my equation for calculating delta S at standard state for the reaction, and then I wrote down my balanced reaction between sulfur dioxide and calcium hydroxide, which forms calcium sulfite in water. After that, I wrote down my standard entropy values for my products, which are seen in the brackets above. Subtracted from that my standard entropy values of my reactants. Each one is just 1 mole, so I didn't need to multiply by any other factor. And then when I plugged those into my calculator, I got negative 160.2 joules per mole Kelvin, which does correspond with the correct number of sig figs, because remember, sig figs for multiplication and subtraction, addition and subtraction is dependent upon the fewest number of decimal places. So in this case, the fewest is 1 decimal place, so I have 1 in my answer. All right, let's move on to number 2. Number 2 states, calculate the value of Q and delta G for the following reactions given initial concentrations and delta G naught at 298.15 K. Just a side note, sometimes you'll just see 298 K and sometimes you'll see 298.15. One is just giving you more precision than the other, but it's not different in the way that you approach the problem. So you have two different reactions, A and B. What you need to keep in mind in these problems is what G is. Sorry, not what G, what Q is. Q is your product concentration over your reactant concentration. And you also need to choose the correct formula for calculating delta G. We have a couple listed in our chapter 20 notes. So use the equation that can correlate delta G naught and Q together to calculate your delta G. So go ahead and pause the video at this point and then check back to see the answer for A. And then after that, I will just give you the answer for B, but I won't walk through all the steps like I do for A. Okay, the first thing I did for part A was set up my Q expression. So that would be my products, which are hydroxide squared, since I have a 2 in the coefficient for hydroxide, and then the molar concentration of lead 2, with 1 on the bottom because my reactant is a solid. In my next step, I set up what my molar concentration of lead 2 was, and that is stated in the problem, so there was no manipulation or calculation I needed to do there. But to determine the molar concentration of hydroxide, I have 2 options. I can either go backwards and find the molar concentration of hydronium by taking the 10 to the negative pH, and then solving for hydroxide by dividing my Kw constant by the molar concentration of hydronium, or I can take 14 minus pH to get the POH, and then 10 to the negative POH to get my molar concentration of hydroxide. Either one should give you very similar answers that you can plug in to the problem. If you didn't think about doing this, go ahead and stop at this point and continue the problem to see if you can finish. All right, at this point for your concentration of hydroxide, you should get numbers close to this value, depending on what constant you plugged in. For kW, if you plugged in 1.00 times 10 to the negative 7, it's right here, then you would have gotten my answer. If you put 1.008 times 10 to the negative 7, you would get something a little different, but they're very close to each other. Whenever you're using a constant on the exam, use the one that's given to you, and I will be grading off of that number. After that, I set up my Q expression to include the molar concentration values that I just solved for, making sure that I do square the hydroxide concentration. And this gives me a Q of 1.0 times 10 to the negative 20. Technically, this is going to be QC. It's going to be our reaction quotient expression in terms of concentration. This is the formula that you should be using to solve for delta G. Delta G equals delta G naught plus RT ln Q. Delta G naught value is given up here. R is a constant. Temperature is given in the problem. And your Q you just solved for in the previous step. So plug those values in and your answer should be negative 2. Let's see, sig figs is 2. So 2.9 times 10 to the 1 kilojoules per mole. And I'm just going to give you the answer for part B, and let me know if you have questions about how I got that. Here is your answer for part B. All right, number 3 asks to calculate delta G naught, delta H naught, and delta S naught for the following reactions using the data table below. I will do part B and give you the answer, and then you can do A on your own and just check your answer. So at this time, go ahead and pause the video and then check back for the answer. For your delta S naught, you should have gotten negative 39.7 joules per mole times Kelvin. Your delta H naught value should be negative 467 kilojoules per mole. Remember, at this point, you need to plug in your temperature and your delta S naught in the correct units, because delta S naught is in joules per mole Kelvin, and you do need to convert that into kilojoules so that these two units can be subtracted from each other. So your final answer after you plug in the temperature of 100 degrees Celsius, which would be 373.15 Kelvin, will be negative 452 kilojoules per mole. Okay, your answer for part A, delta G naught, should be negative 2083 kilojoules per mole. Something that I want you to take into consideration and think about in this problem is that the delta S naught and delta H naught values are both negative values for A and for B. This means that temperature is really the deciding factor as to whether or not a reaction is going to be spontaneous. That negative delta H makes a more spontaneous reaction, but the negative delta S makes a less spontaneous reaction. So that means as temperature increases, the spontaneity of the reaction decreases, and vice versa. As temperature goes down, spontaneity increases. So notice that pattern as we look at our upcoming problems, as well as your problems on the quizzes and exams. All right, so on to question 4. Given delta H naught and delta S naught for the phase change below, estimate the melting or boiling point. This data is for iron, and we're given delta H naught of fusion and delta S naught of fusion. Fusion means that melting is occurring, so that means that you are determining what the melting point is. So I want to remind you of a couple things about phase changes and specifically about melting point. So when a phase change is occurring, there is no change in temperature. The second thing that I want to remind you of is while a phase change is occurring, that means that delta G is 0. So use this information to determine what the melting point of iron is. Go ahead and stop the video or pause the video here. So delta G naught is 0 when at equilibrium, when this phase change is occurring. And we know that the formula delta G naught is equal to delta H naught minus T delta S naught. So I can just plug in 0 for delta G naught and solve for my temperature. I have 0 is equal to delta H naught minus T delta S naught. Adding the T delta S naught portion of the equation to the other side, I get delta H naught is equal to T times delta S naught. Solving for temperature by itself, I have delta H naught over delta S naught, and that equals 1.86 times 10 to the 3 Kelvin. Remember, again, when you're plugging in delta S, you do need to convert joules into kilojoules, which will successfully cancel out the kilojoules between the delta H and delta S and the unit of moles, and it will leave you the unit of Kelvin. Okay, on to our next problem and our last problem for today. Hemoglobin carries oxygen from the lungs to tissue cells where the oxygen is released. The protein is represented as HB for hemoglobin. In its unoxygenated form, just means it does not have oxygen attached to it at that point. And it is represented as Hb.O2 in its oxygenated form. One reason carbon monoxide is toxic to us is that it competes with oxygen in binding to hemoglobin. So we have the balanced equilibrium reaction. Hemoglobin oxygenated plus carbon monoxide yields hemoglobin with carbon monoxide plus O2. If delta G naught is equal to negative 14 kilojoules at 37 degrees Celsius, what is the ratio of the hemoglobin complex with carbon monoxide to the hemoglobin complex with oxygen if the oxygen concentration is equal to carbon monoxide concentration? So refer to your chapter 20 notes and formulas to see which delta G formula you will be using. Just a little hint, you're going to be solving for the ratio by using K, solving for K. Go ahead and pause here and then check back for the answer. All right, so you should be using the formula delta G naught equals negative RT ln of K. K is equal to the concentrations of the products over the concentrations of the reactants. And notice in part A, it gives you some pertinent information that at this temperature, we are considering oxygen concentration equal to carbon monoxide concentration, which means they just cancel each other out, because if they're both 1, 2, 3, 4, no matter what it is, if you multiply the top by the same as you multiply the bottom, then those two numbers can cancel out. So then I'm going to take my delta G naught equation and solve so that I just have K by itself. So I am going to set this equal to, again, negative RT natural log of K. I'm going to divide by negative RT on both sides. So therefore I have natural log of K is equal to negative delta G naught over RT. And to get rid of that natural log, I am going to do base E on both sides. So I have K is equal to E to the negative delta G naught over RT. Now I'm going to plug in my values for delta G naught, my temperature in Kelvin, and then my R constant. All right, I'm plugging in my delta G naught value in terms of joules per mole of the reaction, dividing that by my R, which is 8.314 joules per mole times Kelvin. multiplied by the temperature, which will be 310 Kelvin. Okay, so after I plug everything in, my final answer for K should be 2.3 times, actually maybe 2.30 for sake. 2.29 actually. 2.29 times 10 squared, and this is equal to the ratio of hemoglobin carbon monoxide over hemoglobin O2, which is bad. When you have equal concentrations of oxygen and carbon monoxide, it means that the carbon monoxide oversaturates your hemoglobin and you get really no transfer of oxygen to your tissues. Okay, so this is the end of our practice problems for chapter 20. Let me know if you need any help. I'll be available for lecture and for lab and how I can assist you in preparing for the exam.